Hi, Jesse.
Hey Alan, how's it going?
I'm doing pretty well. How about yourself?
Good. So, what have you been up to?
Last week, we hit this major milestone in our development roadmap, which is recursion. For the first time, we had proven the correct execution of a program that is verifying the proof of another program. And so that was nice. This is something
Could
we've
you
been
could
working
you could
towards
you
for a
slow
while
that
now.
slow that down a little bit? Repeat and slow it down.
We proved the correct execution of a program that verified the proof of another computation.
Right. Continue.
Yeah, this is a important milestone because after you reach recursion, your scaling it becomes flat, right? Because if your computation takes longer than the threshold for recursion, you can always split it up into two different computations and then merge those two resulting proofs into one using recursion. Um,
I'm not sure I got that.
well, in general, the process of producing a proof for a computation scales not even linearly, but we try to keep it as close to linearly as possible. So if your computation takes twice as long, it takes more than twice, but still close to a factor two the time to prove it. But after you reach the complexity threshold for recursion, that scaling factor all but disappears because you generate two separate proofs for your long-winded computation in parallel, uh, one for the first part, one for the second part, and then in the second step, you merge those two proofs together using a proof of correct verification of proofs.
But what? Why two? Why not 10?
Why not 10? It's perfectly possible to do it in 10 pieces as well. Uh, the point is you're not gaining anything if you do it only once.
Right. But you do gain the more you do it.
Um, well, since the process of verifying a proof is still relatively expensive to prove, you probably don't want to verify more than two proofs in the process of producing one single proof, because you're spending more cycles than necessary. So you probably want to turn your long-winded computation into a tree, and then with 3 levels, 4 levels of recursion, you can prove something between 8 and 16 times the length that you would otherwise not use recursion for.
Can we break this down in terms of an example? So can we say that there's an example computation of let's say one plus one or one plus one plus one, and can we approach that with recursion, or maybe you have a better example?
How about the factorial?
Hmm.
What's the nth factorial number? Or perhaps better yet, what's the nth Fibonacci number? Because the reason why this second example is a better example is because you can pause it in the middle of running this computation. As long as you collect two consecutive numbers, you can continue that process. And so, in order to split this very long computation, say we're computing the 2 to the 100th
So okay, so
Fibonacci number.
let's dumb this down a little bit. And not everyone's familiar with Fibonacci sequences. So what's a Fibonacci sequence?
It starts with 1 and 1. It's a series of numbers, and the nth number, where n is greater than 2, is defined as n minus n I minus 1 plus n I minus 2. So it's 1, 1, and then you take the sum of the two previous numbers, that would be 2. And then you take the sum of the two previous numbers, that would be 1 plus 2 is 3. Then you take the sum of the two previous numbers, that would be 2 plus 3 is 5, 8, and so on.
Right.
And if for whatever reason we need to compute a Fibonacci number of a very, very, very large index,
But the only way to compute it is to compute every element until n.
as far as we know, but maybe there's a clever mathematician out there who can find a shortcut. But in principle, problems can exist similar to the nth Fibonacci number problem, where the only way really is to compute it sequentially.
Okay.
And that may have been a very simple example, and it certainly highlights the value of being able to cut your computation up into pieces. In one proof, you prove that you computed the 10th and 11th Fibonacci numbers correctly. In the second proof, you prove that going from the 10th and 11th to the 20th and 21st was done correctly, and so on. And in your 10th proof, you prove that the 100th Fibonacci number was computed correctly. And once you bundle all those proofs together and prove the correctness of those proofs, then you have a proof of correct computation of the 100th Fibonacci number.
But you're jumping in between, but we would have to prove the correctness of every single computation, right?
Yes.
Okay.
Um,
And so,
go ahead.
and where does recursion come in?
Recursion comes in when you bundle those separate proofs together into one proof.
Okay, and so what would be the separate proofs? Why did you start from you said 10th to 11th, but what about the proofs before that?
No, the very first proof in this sequence of proofs is a proof of correct computation of the 10th and 11th Fibonacci numbers from the first and second. So this is still a computation that runs for a bunch of clock cycles, and you need to prove that. And then you have a proof, and then the next part of the computation, the claim there is, given the 10th and 11th Fibonacci numbers, these are the 20th and 21st Fibonacci numbers. That also runs for some clock cycles, so you need to produce a proof for that. And then you have two proofs, which you can merge using recursion.
Okay, but how is that faster in this case?
Because if you were to prove the correct computation of the 20th and 21st Fibonacci numbers directly, it would scale superlinearly.
Okay,
So
and so
it would take more than twice as long.
more than twice as long as the original computation.
No, more than twice as long as proving the correctness of one segment.
Okay. So walk me through it one more time.
So you want a proof of correct computation of the 100th Fibonacci number,
Right.
and there is a program that computes the 100th Fibonacci number, and okay, you can probably run it on your computer, but what if instead of 100 we ask 2 to the 100? What's the 2 to the 100th Fibonacci number? I might be able to give you the 2 to the 100th Fibonacci number, but then you don't have a way of verifying that it was computed correctly.
Right.
And so I want to give you a proof that it's actually correct.
Right.
So what do I do? In my zero knowledge virtual machine, I implement this algorithm to compute the 2 to the 100th Fibonacci number. It outputs a proof, and that proof should convince you.
But
But
okay.
this is too complex even for me to run on my supercomputer cluster.
because of this scaling of a bit higher than
Exactly.
2.
And moreover, the without recursion, the production of proofs doesn't parallelize very well. So I'm stuck to sequentially generating a proof for this. So what I'm going to do instead,
But hang on, I follow you up until now, but I forgot what does the 2 relate to? What is the 1? Or it's the scaling is a bit over 2 times what?
the one would be producing a proof for the 2 to the 99th Fibonacci number.
Okay, and why are we comparing it to that?
To illustrate the nature of scaling. Because the number of cycles to go from the first Fibonacci number to the 2 to the 99th is the same as the number of cycles to go from the 2 to the 99th to the 2 to the 100th. So it's a point in the middle of this very long-winded computation that cuts it neatly into 2 segments.
But how is it neatly 2 segments? Isn't it at the end of the segment?
Is what at the end of the segment?
The 2 to the 99th?
It's at the end of the first segment and at the start of the second.
But you say you cut it cleanly. Wouldn't cleanly be 2 to the 50th? Like halfway?
That's not halfway.
So what am I not understanding?
Exponentials.
Okay.
Half of 2 to the
So say
100
more.
is not 2 to the 50. Half of 2 to the 100 is 2 to the 99.
But we're still talking about a Fibonacci series. I thought we were talking about where we are in a series of 100 numbers, and that we were calculating the first 99 elements.
Yeah, I made the problem a little more complex to illustrate that it's infeasible for you to verify the computation directly. And so I went from calculating the 100th Fibonacci number to calculating the 2 to the 100th Fibonacci number, because there's no way you could hope to verify this unless with a proof.
Okay. Okay. So we're talking about 2 to the 100th. Okay. Now I'm understanding. Okay. So then there's a huge gap between the 2 to the 99th number in the Fibonacci versus the 2 to the 100th. Okay. And that's 2 in terms of computational complexity.
The entire bridge from 0 to 2 to the 100 is 2 times from 0 to 2 to the 99. Yes.
Okay. So back where we left off.
Right. I want to give you one proof of correct computation of this 2 to the 100th Fibonacci number. And I could, in principle, run my own machine for 2 to the 100 cycles. And in fact, it would be more cycles because you have to do some bookkeeping with the integers that you're manipulating, and produce a proof directly. But that is more than twice as expensive as producing 2 proofs of half the range.
Okay. Well, the part I understood previously is that that calculating the proof for n minus 1 would be half of calculating the proof of n. Right?
No.
I'm not sure anymore this is a good idea to do
No,
live. No, okay,
let's
explain.
just start the call over again.
But explain.
I don't know
I'm
which
trying
words
trying
to
try,
use that I didn't already use.
I'm trying to understand why you say half now.
As opposed to?
Um, well, you're saying you can take two proofs and then
Yes.
merge them, and then that the result of doing that will be half in terms of complexity of doing it straight away. Is that correct?
No, that's not what I said. Doing it straight away is more than twice the cost of producing the proof for one segment individually. And so combining two proofs, that's a constant cost, and so we're allowed to ignore that. And so we're comparing the cost of proving
Hang
directly
on.
versus
Repeat the beginning again.
I don't know where the beginning was.
Which 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 part is more than two?
Producing the proof directly.
Okay, producing the proof directly is more than two times the complexity
Producing a
of
proof for half
the
the
mer.
segment, for half the entire computation.
Computing a proof for the entire segment is more than twice the complexity of proving half the segment.
Yes.
I don't know. That sounds quite reasonable and understandable. So go on.
Well, that's how I'm going to produce a single proof of the correct computation of the 2 to the 100th Fibonacci number.
But if you take so producing the full is two times producing half, but you need two
No,
halves,
producing the
and then
full
you
is more than 2 times producing the half.
producing the full is more than two times producing the half. Okay. So where does the benefit show up, or how do you calculate the reduced complexity that you end up with?
It's less work if I were to do it on a single core. And by the way, I can distribute the proof production of the two segments on two different computers. So I can benefit from
But but
parallelism.
when you but when you compute the proof on half, you still need to compute the proof on the other
Yes.
half. And if computing the proof on the whole is, let's say, 2.2
Yeah.
complexity, what is the proof of half?
1.
So what you end up with is 1 plus 1 compared to
Correct.
2.2, let's say. See, that's what I was after. Okay. So that sounds kind of marginal, though, but I'm sure it's not.
It's mind blowing. No,
Okay.
because
Because you can repeat it on
exactly,
top of each other, and that's the
exactly.
recursion. Okay. But at infinitum, like you can just split it up into 1,000 parts and then,
Exactly.
okay, that sounds like you're cheating some law of the
It does,
universe.
doesn't it? Um, yeah, the way we get around these laws of the universe is there is a degradation in security. So, firstly, these proofs are only computationally secure, not perfectly secure, and by secure I really mean sound. So it's possible that I happen across a collection of bytes that convinces you, but is actually the claim is actually false. it's possible, and we know exactly what that probability might be, and it would be 2 to the minus 150 or something ridiculously small like that. Um, and once you start stacking these proofs on top of each other, this number starts increasing. But we make sure to engineer it such that this number is always very small.
So, so going back to my made up example of the 2.2 compared to the 1 plus 1, if you split it up into let's say four, are those 0.25 each? Like, will it still amount to one? Because then I'm not seeing the
No,
recursive benefit.
I'd say if you want to split it up into four, then you're comparing 1 plus 1 plus 1 plus 1 to 5. And if you split it up into
Okay.
8, then you're comparing 8 times 1 versus 12.
Okay. And this recursion is something you knew was possible. You just needed
Correct.
to build it. And is this something that's done in other cryptocurrencies, or is this really something esoteric from the original crypto field?
Um, let's see. Um, some rollups have recursive proofs. Starknet, I think, was the first one to have them. Um, it's been known in the industry for a while that recursion is the holy grail of proof systems. So plenty of teams have been working on it and are working on it. In terms of layer one projects, I think only Nina has them at this point. Um, yeah, just that.
And so, what is the main thing that it cuts down on? It's how long it takes to compute a proof.
It's how long it takes to compute a proof. Let's see. I'm not sure that
Ha.
that question is designed to provoke the answer you're after.
Okay.
Can you ask for the same thing in a completely different question?
Well, you're saying it's the Holy Grail, which kind of signifies that it's something that's difficult to achieve, but once achieved, it unlocks huge potential. So I'm try to understand how would one measure that potential?
I think the only way to measure those potentials are through their applications, and so we should talk about applications. One application is
So how does Neptune look with and without recursion?
without recursion. You have a history that continues growing forever, and your initial block download grows with the age of the network because you have to download more blocks and you have to store them, and the synchronization time grows with the age of the network because you have more blocks to verify. And with recursion, where every block proves the correctness of the previous block, which, by the way, contains a proof of correctness of its predecessor, with recursion, you only need to download the most recent block, and by verifying the proof in there, you can verify all of history straight down to the Genesis block. And so the cost of the initial block download is much smaller because you don't care about most of the historical blocks. You only care about the recent blocks, and you don't need to store them either.
So in a way, the like the what blockchains like Ethereum are doing nowadays. Like they are only uh, like we talked about in the previous episode, is that it's difficult to run a full node because of the size of the database, and so many don't end up running a full node. They just carry like the last sort of the top of the blockchain, the last couple of blocks, because that's easy enough. But that's sort of a concession that people make. Whereas this would allow everyone to not have to make that concession um, because of
because of recursion. Yes,
recursion.
exactly.
Okay, wow, that's. I wonder if that's maybe something that's even forgotten that was a
Yes.
concession.
And oftentimes when I explain this to people, they say, "Yeah, you just download blocks until the most recent checkpoint, and that's it. What's the big deal?" The checkpoint being what was
And so
the
what?
block that was signed off by whoever is developing the protocol.
And so what is the big deal?
Well, you're trying to eliminate trusted parties. And if you trust the developers to sign off, then you're you're throwing out the baby with the bathwater.
I get that, but that's I mean, and I guess in like theoretical context, that's yeah, a valid argument. But if I go and I buy a piece of property from somebody and he shows me he's, I guess he owns it and then the previous owner, but we don't need to go back to the origin of Earth.
It puts power in the hands of whoever signs off on these checkpoints, because they can act as arbitrators in case of a dispute. If there are two different and contradictory views of the history of the blockchain, um, if checkpoints are in place, uh, the judges who sign off on these checkpoints can engineer a consensus away from the consensus rules. And so, if there is a high value dispute, then both defendant and plaintiff, or is the defendant the plaintiff? Maybe not. Both parties in the dispute have an incentive to influence these checkpoint signers. It's an attack
Right,
vector.
it's an attack vector.
But yeah, if you're just buying a pizza,
Cool,
probably fine. Nobody's going to care.
cool. Yeah, I guess it's one of those things that I've not thought too deeply about. But then I guess if you have this theoretical context, it's something that you would want to optimize, and then apparently you can, and that's what you guys are doing, and you go all the way that everyone can always. I mean, what it reminds me of is how you were explaining that article you wrote. I forget actually which one. If it's the one about Ethereum not being objective or another one. But basically, your framing of the whole discussion of blockchains is that blockchain is basically a way to um, to align on what is the sequence of transactions all the way to the genesis block. That's always the question to be answered, and the blockchain is just the only way we found to figure that out in a group of
Yeah, the
people
Genesis
that
block
don't
is
know
the
each
only
other.
thing you take on faith. And if you don't take the Genesis block on faith, you're taking something else on faith. And let's be open and clear about what you are taking on faith. And if what you're taking on faith is the most recently signed checkpoint, then you're basically elevating individuals and not code to arbitrators.
Yeah, I think that's just such a. I mean, it's probably so obvious that it's funny to you from that I'm like grappling with it, but I think that's such an interesting way to frame the whole blockchain space and a way to assess also other solutions in that space. Cool. Shall we
That sounds like
leave
a
it
good
there
point to
and
wrap
wrap
up.
up for this week?
Nice talking to you.
Cool.
See you next
Yeah,
week.
likewise. See you next week.